Okay, so I'm going to get started a little bit behind because I had some trouble with getting access to my backpack, which is in another classroom, and I've had to send someone up to go retrieve it. So today's class, we're going to be talking about the modeling process, which is going to be sort of the overarching structure for the material of the class. Now, this is a big topic, and it's one that I've covered elsewhere in much greater level of detail. And for those who are interested, I'm going to refer you to that broader coverage so you can find out more information if you're interested. Today's class, I'm going to be covering a few very important issues that are absolutely essential to keep in mind when you're pursuing projects in this class and when you are undertaking modeling more generally. Bear in mind that there's much more detailed coverage of this material in two successive lectures comprising about 3 hours in total just on this topic. And I'll see if I can provide you the links to that material, okay? For those who are interested, it does provide discussion of possibilities, documentation, suggestions on a set of issues that you should be thinking about, including in your model, things to keep in mind when you are designing your model to make sure you're not accidentally forgetting things. So here we are just going to be covering the bare essentials having to do with the modeling process. So I'm just going to switch over so that remote individuals can see details on the on my desktop here, and I'll be starting up. So, overview of the modeling process. So, the modeling process that we're talking about here relates to dynamic models which are used typically in an interdisciplinary environment. We're building models here which inform an understanding of a wide variety of domains. Some of those domains happen to be conducted in technical areas. So as I've mentioned, types of models that we're building in this class can perform very useful duty when reasoning about performance. Thanks so much. Performance of computer systems, for example. They can help us reason about behavior of large sets of servers, behavior of complex network architectures, the impact in terms of overall system performance of adding in new transportation options, say transmission means between point A and point B in a network. So putting into place new network segments, as it were, whether it's via Ethernet or wireless. With different baud rates, how does that affect the routing, the overall performance of routing across the entire network? But a lot of the uses of these models lie in areas outside of computer science. They're tools, they're scientific tools for answering questions about complex systems. And complex systems pop up in all sorts of domains of human activity. So typically we are working in a modeling process in the context of an interdisciplinary, a team which involves not only computer scientists, sometimes physicists, sometimes people who are from social sciences, health sciences, transportation planning, all sorts of different backgrounds. So you're getting people coming to the table who may not all be familiar with how you build these models, but need to use the results of the models, need to use the statistics generated by the models or the recommendations coming out of the models. Typically, this is an ongoing process of refinement. So you're building a model, you're getting feedback on it, you're comparing it to empirical data, observed data, and deciding, is this an adequate model? Do we need to extend it in certain ways? And it's best undertaken where possible where you're doing the modeling, but you also examine the impact of putting into place sample interventions. You actually try to change something in the real world based on recommendations. And you try to compare what you see in the model with what you see as a result of that intervention. So you may try, for example, to examine the impact of, based on model output related to traffic flow, changing the signage at a certain place, or opening up an extra lane using the breakdown lane during certain periods of the day. And you compare it with model results. The model there is predicting a counterfactual. It's been predicting something which hasn't been observed, and now you actually try perturbing the system and see if it accords with what the model predicts. Because again, a lot of the uses of these models as sort of operational theories, they help us understand what's the impact of things we haven't directly observed. Quite different, ladies and gentlemen, from statistics in that regard, which are often, when you collect them, they require observation of a situation that's been in process. Here the models are because recent about a situation that hasn't been observed directly. So these models are best used when we can observe results of implementation and where we can use them to influence data collection. Later in the class, I may share some stories where the model has not accorded with data. We've actually observed model results, and they don't match data. And we've been puzzled why. We futz with things in the model, change parameter values, change the structure of the model, and it still doesn't accord with the data. And these have occurred over decades of my modeling experience. Gone to the stakeholders and talked to them about this, and they tell us actually the data is wrong. It's the data that's at issue. The data had it was reclassified. They were using different classifications for these than they were for these years. And the reason it didn't match is because they changed the definitions of what was being collected, for example. But more commonly, modeling influences data collection because it helps us to identify pieces of data that are particularly valuable. Valuable for improving our understanding of what's likely to happen as a result of a change, or improving our understanding of the relative trade-offs between two different strategies, two different decision points, okay? So often we try to iterate the modeling with it's best if we can have the modeling inform data collection, inform what data are we collecting and how frequently, because that can allow us to improve our modeling better. So models are living documents here. Now, I will note that in different areas of the modeling space, particularly agent-based modeling and discrete event modeling, two of the types we'll be talking about this semester, we've been dealing with situations where there's an attention to the final model as sort of the main product of modeling. It's the main point of value. It's the artifact itself that's viewed as a value, this model which you can then use. In system dynamics, there's more attention to the modeling process. The idea is that people are changed through the modeling process. The participation in the modeling process is often the more transformative thing. The idea being that even if the model were to disappear in a puff of smoke following the conclusion of the modeling process, you still would have gotten tremendous value because how people think about the system has been fundamentally altered. What they think of as the key points, their understanding of what the most important variables are to collect data on or to modify, their understanding of how the system works has been deeply modified by the modeling experience. System dynamics puts us on this, but to some degree it's true for agent modeling and for discrete event modeling, okay? So the notion of modeling as transformative, we'll get a glimpse of that in system dynamics in a little bit. So I'm just going to